we continue our discussion on the nearest neighbor rule. To summarize, what we did is the following. To a test sample, new sample, we find its k nearest neighbor training sample. Usually k is chosen odd, and then find out the majority class, majority category among the neighbors, and put it into that class. As you can understand that if k is odd, if you have two classes, one of the class will always be the winner. There cannot be a tie. In more number of classes there can be tie. If there is a tie, you can arbitrarily put in any of the class. The special case where k is 1 is called the nearest neighbor rule. So, here is the pictorial description. So, to classify x, we take in this case the one neighbor, only one more point, in this case 2 neighbor, in this case 3 neighbor. Okay. And for example, in 3 neighbor the plus class is the winner, majority, it has 2 to 1, and we put x as, classify x as plus. Okay. For the case of one neighbor, this has a nice geometric interpretation called the Voronoi diagram or Voronoi cells. So, each of these plus are my training points. Each of these plus as my training point. Okay. So, around I tile, or it is called a tessellation. I split up my entire feature space into small cells, What are these cells? If you take a point in one of these cells, this particular plus, so note that corresponding to every plus we have a cell, every plus belongs to a cell, and there is no other plus. One cell has only one point, and that is that plus. So, what is the definition of these cells is that if you take any point in this cell, the closest among these training set, the plus points, is this. So, if you take any point here, suppose I take this point and you take distance to all the training sets, the closest would be the representative point of that cell, would be the point of that cell. So, if we look at it the other way round, given every point, you define its Voronoi cell to be all points whose nearest neighbor is this given point. Okay. Is this, note that each point in the these Voronoi cells, they define some kind of a equivalence class, a partition. They define a partition. Okay. So, if I use my nearest neighbor classifier, one nearest neighbor classifier, so to say, all I need to do to classify a new point is to check which Voronoi cell it belongs to. Okay, and look at the class of the point corresponding to that cell. Note that every training point will belong to one set and will define a set. No other training point will belong to that particular set. It is as if the region of influence of this point. You might wonder why the region of influence is not circular. It is because the shape of these cells depend on the shape of the distribution of the other points. Okay. So, here the Voronoi cells are closer, where here they are spread apart, because there are other points here which pull them. Okay. So, it is this this Voronoi cell is equivalent to the 1NN rule. You just put it into the same class as the point. Okay, so this is the geometric interpretation. You will need it in some future discussion. So, if we come back to the general KNN rule, what it did was the following: take a neighborhood, vote among the points. So, there is 2 here, 2 here, whichever wins the vote is that class, is the class of the new point. I can make a slight modification to this. Instead of just equal contribution to the vote, I can say that points which are closer have higher contribution to the vote, have more voting power, to the point which are closer to the new point which I want to classify. Okay. So, here this minus has more voting power than these 2 points. So, this rule is known as the distance weighted k nearest neighbor rule. Okay. So, basically FQ is the class, FQ is the class, sorry, FQ is the class. It is some weight function, it is the class of the distance, where V is the neighborhood. This is the normal KNN, and I can have a distance weighted KNN. In fact, what I can do is that not just weighted by the distance, not just inversely proportional to the, sorry, not just inverse distance I can use it. I can use a general weighting function. So, called a kernel function. So, I can maybe use something decaying like this. So, a function which, let me see if I can draw it here. So, as distance increases, it goes down, its contribution to vote goes down. Okay. So, this is an example of a kernel function. Okay. So, this technique is an generalization of the k nearest neighbor technique. It is called the Partgen window technique. It is called the Partgen window technique, where we have a either inverse weight, inverse distance, or some general function, some Gaussian kernel or something. Okay, in the distance weighted KNN. In fact, what I can do is to sort of extend this rule to classify problems which are not just classification, but predicting some continuous values also. Okay. So, I want to, for example, present the temperature of tomorrow. Sorry, I want to predict, sorry, not present, I want to predict the temperature of tomorrow depending on other values like the pressure, rainfall and so thing. and my training point consists of temperature of say 10 years in this region. So, what I do, I find k other similar days who have a similar pressure rainfall profile and what their temperature are, and I predict temperature of tomorrow is the average of all these k neighbor temperatures, maybe an weighted average if we consider distance. Okay. So, the KNN is a general principle beyond classification also. Okay. So, I guess this is clear. What you can possibly do is that you can take some example or say something like this. You assume that there are 3 classes and each of the class sort of is, you make an assumption, do not use it actually, it is non-parametric. So, I am not going to assume they are Gaussian. Just for generating the data, you assume mu 1 sigma 1, mu 2 sigma 2, mu 3 sigma 3 are the 3 Gaussians, and you randomly use these Gaussians to generate say 1000 points. Okay. And now they have belong to class 1, 2 and 3, I denote class as integers, and for a, so you have 10,000 example, 1000 examples generated from 3 Gaussians, class 1, class 2, class 3, and you take a new, this is a computer experiment. So, you generate these points, take a new point x, some new point x, and take some value of k, say 3, and apply the KNN rule, k nearest neighbor. First the non-weighted version, then the weighted inverse distance weighted version, and see how much accuracy you get, how well, how many times it correctly classifies a new example. Okay. So, you can do this experiment using writing a small program in any language, and you will see the effect. Okay. So, if you are trying to write this program and actually do, you will face the following issues. You have to choose a value of k. For 2, 3, 5, 7, what value? You have to choose a distance measure, because everything is nearest neighbor is defined only when a distance is defined. You have to choose what size training set you want, how many points to keep in the training example. And that will depend on how much computational complexity you can afford, how much time you need to classify, you can afford to classify. Okay. So, we will just quickly discuss some thumb rules, there is no theory, some thumb rule to decide on these parameters. First, the value of k. If k is too small, your neighborhood is very small. Okay. So, noise and other, for example, let me tell this. See, we would probably expect this x to lie in this plus class, okay, or actually it is in the boundary, so it can point. So, if we choose k to be only 1 nearest neighbor, you get minus as the class. If you choose k to be 2, you get a 50-50. So, here it depends, if it is k is small, it depends too much on the local property. Okay. Similarly, if k is too large, it depends on broad range. Okay. So, what is a good value of k? Actually, let me do it this way. Noise, if it is a large k, it is too global. Can any of you tell you if k is equal to size of the training set? What does this mean? You go back to your previous slide. If k equal to size of A, k nearest neighbor is gives the probability of nothing but the prior probabilities of the classes. Okay. So, if it is too large, this may be the case. So, there is really no theory to decide what is the correct value of k. Some rule of thumb are here. If one rule of thumb is this, when n is the size of training set. Some other people take it this way. Okay, take it this way. So, this is option, this is option. You do not really know which one will work. This is an open problem in data mining. Nobody really knows. So, any of you, if you can find a good solution to this problem, that will be quite a contribution to data mining. What about the distance metric? So, many possibilities are there. What kind of measure should I take as a distance? I list here a number of distances. Okay. The most common is Euclidean. A little bit of generalization is this. So, this is this plus this is Manhattan or city block. Okay, you can have a weighting factor q called the Mulholland-Beach distance, this one. Okay. Others are also possible. Some factors to be noted: scale, what do? You normalize each feature value. Okay. So, it becomes between 0 to 1 or minus 1 to 1 rather. Z score is the normalized attribute value. Note that many of these distance measures, they fail when the number of attributes are high. Okay. So, if I have so sparse, if the many of the attributes have 0 value. So, you can see here distance between these two vector is this Euclidean, here it is this. Whereas these two are very similar, these two are very similar, this is quite a far apart, same d value Euclidean. All right. So, so you have to take care of this. This is a very common problem, applying nearest neighbor to high dimensional data without properly choosing a distance function. Many times it depends on the domain. How do you define distance in nominal attributes? Do this. You define how many times certain attribute value is associated with a class. Okay. And use that. All right. So, you just look at the definition. I have defined it. So, this is this, and C is the number of output class. This is defined this way. So, suppose some attribute A is say low, medium or high, like that, nominal valued. If you go back to our discussion in data preprocessing, we discussed some of this. That is why I am not discussing this in details here, you should read that again. Okay. So, this is for heterogeneous. So, with this I stop this lecture, I complete my discussion of the distance function. We will go into other considerations of nearest neighbor which are important in the next lecture. So, thank you.